Here we're going to start to branch out and look at different types of indeterminate forms. So here we're looking at a form of 0 times infinity. Now if we look at it, what happens as x goes to infinity? Well, this part, x, that's going to infinity. As x goes to infinity, x minus 1 over x plus 1, so that's a rational function. As x goes to infinity, that goes to 1. And then we're taking the logarithm of something going to 1, so this thing is going to 0. So we have the first piece, the first factor, is going to infinity. The second one's going to 0. So we have something going to infinity times something going to 0. Something's blowing up, whereas something's going to 0. And I'd like to know which one wins out. Does this one go to 0 faster than this one blows up? Or does this one blow up faster than this one goes to 0? Or are they sort of going at roughly the same rate, in which case they balance out and have a value of a limit which is some non-zero finite number? These are the questions that I need to be able to answer. How fast does x go to infinity relative to the logarithm of this rational function go to 0? It could be 0, could be infinity, could be anything in between. The problem is I don't know at this point, just that it's of type 0 times infinity. I don't know what the answer is. I have more work to do, and the more work is L'Hopital's rule. But you might observe that L'Hopital's rule doesn't apply directly in this case. It's not of type 0 over 0 or infinity over infinity. It's of type 0 times infinity. So what we're going to have to do is try to maybe rework it so it is of type 0 over 0 or infinity over infinity. One way to do that is to say, well, let's take that logarithm and leave it up top, and let's push that x downstairs as a 1 over x. Now what's happening? Well, as x goes to infinity, the top goes to ln of 1, goes to 0. The bottom goes to 1 over x, where x is going to infinity, so that goes to 0. So it is of type 0 over 0, and now we can apply L'Hopital's rule. So we had a little bit of adjustment to make first, but now we're in the situation where we can apply L'Hopital's rule to it. So this is going to be the limit as x goes to infinity of derivative of the top. Okay, so that's 1 over the inside, so it's the reciprocal of the inside function, times the derivative of the inside. That's the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So I had to use the quotient rule to differentiate that inside function as I worked on the top. And now I put that all over the derivative of the bottom function. That's the L'Hopital's rule part. So that's negative 1 over x squared. Now I have a little bit of simplification to do before we can figure out if we can work out this limit or not. So one of these cancels with that one. I have an x plus 1 minus an x minus 1, so that becomes a 2 on the top. I have an x minus 1 times an x plus 1. And that negative 1 over x squared, so that x squared comes all the way up with a negative, so it looks something like this. I see that that's just now a degree 2 polynomial over another degree 2 polynomial, x squared minus 1. And the ratio of 2 degree 2 polynomials as x goes to infinity is just the ratio of their leading coefficients, or negative 2. And so there's our answer. We get an answer of negative 2. So let's just look at this by throwing it into our favorite graphing utility. So I'm going to put the function in and see what it looks like, and we see that as we head off to infinity, the function looks like it gets closer and closer to negative 2, so it has a limiting value of negative 2. And that's precisely what we found. We found that value of the limit. Okay. So again, if you're faced with an indeterminate form of type 0 times infinity, try to convert it to one where L'Hopital's rule applies. Let's look at another example. This is of type infinity minus infinity. So we have as x goes to 0, this goes to infinity. As x goes to 0, this goes to, well, it depends on which side of 0 you're coming from. It's either positive or minus infinity. What's happening here? 1 over infinity minus something going to infinity minus something going to infinity. What does that go to? Well, it all depends. Is this one going to infinity at the same rate this one's going to infinity, so they sort of balance each other off, or is one going to infinity faster than the other, in which case there's this increased spread in their difference, and so the difference goes to infinity. We don't have any information at this point other than just the type is infinity minus infinity. It all depends on how fast each one of them is going to infinity. So we need to try to see if we can get L'Hopital's rule to apply here. So the first thing to do is, instead of looking at it as a difference, try to look at it as a quotient, so we can apply L'Hopital's rule. So I write the difference as a quotient now, and it's of type 0 over 0, so we can apply L'Hopital's rule. So that's the limit as x goes to 0 of derivative of the top is cos x minus 1. Derivative of the bottom, I have to use the product rule, so that's sine x plus x cos x. Now as x goes to 0, the top is going to 1 minus 1. Okay, so that's going to 0. The bottom's going to sine of 0, 0 plus 0. So that's going to 0 as well. So we're of type 0 over 0. So we can use L'Hopital's rule again and look at the limit as x goes to 0 of derivative of the top is negative sine of x. Derivative of the bottom is cos of x. Product rule on the x cos of x, so that's plus cos of x minus x sine of x. As x goes to 0, the top's going to 0, the bottom's going to 1 plus 1 minus 0, so the bottom goes to 2. So the limiting value is 0 over 2, or 0. So we get a value of 0 for our limit in this case. Let's just have a quick peek at this by throwing it into a graphing utility. And we see that as x goes to 0, our function values get close to 0. So the limiting value is 0. Now, it's a pretty cool function. It's got lots of interesting behavior, but the thing we were focused on is what was the limiting value at 0. And in order to figure that out, we had to apply L'Hopital's rule twice in order to get the value of the limit. Okay, let's look at one more example. Now there's a few more indeterminate forms that we haven't seen yet, and that's 0 to the power of 0, infinity to the power of 0, or 1 to the power of infinity. So that means if the base function is going to 0 and the exponent's going to 0, then what is the limiting value of the function itself? We've got 0 raised to the power of 0. What is it doing? Well, we don't have enough information to figure that out. It all depends on how fast the base is going to 0 relative to the exponent, similarly for these other types. So how do we deal with these? Well, we can use our good old friend the logarithm, because it helps us convert exponentiation to products. And we know how to deal with indeterminate forms, which are in sort of the product form 0 times infinity, because we can convert that into a quotient and use L'Hopital's rule directly on type 0 over 0 or infinity over infinity. So that's our key here, is to use logarithms. So let's have a look at this example. As x goes to 0, the base, which is cosine of x, that goes to 1. So this is of type 1 to the power of, well, as x goes to 0, 1 over x squared goes to infinity. So this is of type 1 to the power of infinity. So what is this? Is it 1? Is it 0? Is it infinity? At this stage, we don't know. We don't have enough information. So what's actually going on here? Well, cosine of x is going to 1, but as x gets close to 0, cosine of x is going to 1 from below. It's going to 1 from values slightly below 1. So we can think of cosine of x as always being a little bit below 1, getting closer and closer to 1 as x goes to 0. And the exponent is going to infinity. So we've got a number going to 1, which is always slightly less than 1, to the power of something that's blowing up. So what's it going to? Well, you may think that 1 to the power of anything is 1. Well, that's true as long as the exponent is a finite number. Because here we have that cosine of x is slightly less than 1. So you have a number that's slightly less than 1 being raised to a higher and higher power. So that number is getting closer and closer to 1, but being raised to a higher and higher power. And so you maybe expect that this should be 0, because a number slightly less than 1 raised to a large power is really small. So maybe a number slightly less than 1 going to 1, raised to the exponent going to infinity, might be 0. So is it 0? Is it 1? We have to find out. And in fact, we'll see that it's actually a number between 0 and 1. So let's have a look. So what do we do first? Well, I'm going to let L be the value of this limit. I don't know what it is, but I'm going to call it L. And the reason I'm doing that is because I'm going to want to work with L in an equation in a second. Namely right here. I'm going to now look at the logarithm of L. So in other words, I'm not going to be content with just finding the value of the limit. I'm actually going to go and work what the value of logarithm of the limit is. So that's my first step, is to take the logarithm of both sides of this. The reason I'm doing that is because I want to get rid of that exponent and I want to rewrite it as a product. Now, can I switch the logarithm and the limit? Well, that really depends on whether the logarithm is continuous at the value of this limit. Now, we don't know the value of the limit, but the logarithm is continuous on its domain, so if this limit is in its domain, then we can certainly switch them. So we're going to switch them, and we'll see in the end that the value of the limit is actually within the domain, so this step will be justified at that point. Right now I'm going to take the logarithm, push it through, logarithm of cos x to the power of 1 over x squared. The exponent will come down, and it'll leave me with the logarithm of the cosine with a 1 over x squared out front, so that means we've got an x squared on the denominator. Now, what is this? Well, as x goes to 0, cosine of x goes to 1, ln of 1 is 0, so this is of type 0 over 0. We can now apply L'Hopital's rule. So that was the goal here, was to try to figure out how I could manipulate this expression, or this limit, to get something that I could apply L'Hopital's rule to. Now I'm at a stage where it's of type 0 over 0, I can apply L'Hopital's rule to it. That's the limit as x goes to 0. Derivative of the top is 1 over cosine times the derivative of the cosine, which is negative sine. So it's negative sine x over cos x. The derivative of the bottom is 2x. So I can now just rewrite this, simplify it a little bit. So that's negative sine x over 2x cos x. Now what do I do? Well, as x goes to, it shouldn't be infinity, I'm not sure why I wrote that there, but it's as x goes to 0. This top should be, well, that's going to 0. So that's 0. The bottom's going to 0 as well. So it's of type 0 over 0, so we can use L'Hopital again. The limit as x goes to 0, the derivative of the top, that's negative cos of x. The derivative of the bottom, that's a product rule, so that's 2 cos of x minus 2 sine of x. And now when we work out the value, the limit as x goes to 0, the top goes to 1, the bottom goes to 2. Actually, the top goes to negative 1, the bottom goes to 2. So we get a limit of negative 1/2. Now what does this mean? Notice that it's ln of L that we've just worked out the limit, the value of, sorry, not the limit, the value of ln of L. And so that means that L is equal to e to the negative 1/2. And so there's the value of our limit. We have that the value of this limit here, limit is cos x to the power of 1 over x squared, is e to the negative 1 over 2. That's kind of cool, actually, if you think about it, because the function we started with was nothing more than a cosine function and the reciprocal of a quadratic. And yet somehow the natural number e popped up in there. Kind of a cool relationship between cosine and the exponential. And in fact, you'll see in your later math courses that there is an actual deeper connection between cosines and exponentials. Trigonometric functions in general, sines and cosines, and the exponentials, functions of base e. At this stage, it might be worthwhile pointing out that although we used L'Hopital's rule twice here to get our result, this second one wasn't actually necessary to apply L'Hopital's rule. We could look at it in another way. So here's an alternate way to look at that second limit. The limit as x goes to 0 of negative sine x over 2x cos x. I can split this up. Okay, I'll bring a factor of 1/2, negative 1/2, and then I'm going to group the sine x on the top with the x on the bottom, and then I'll just leave the 1 over cosine x by itself. Now the reason I've done this is because we know the value of this limit. Sine x over x as x goes to 0, that has a value of 1. And that's really the issue here. That's the x here is making the denominator 0, and it's the sine x that's making the numerator 0. So grouping them together like this and getting the value of 1, so using a previously known limit, we get immediately that the value of this limit is 1. Okay, the 1 over cosine x, that also goes to 1 as x goes to 0, so we're just left with the answer negative a half. And there we go. So the key here is to note that as we're progressing through calculations involving these limits, we're using L'Hopital's rule when we get 0 over 0. Some cases we may just find that it's quicker to observe that, hey, it's a previously known limit in there, and then quickly jump and do this alternate method. So things to be aware of when you're actually doing calculations. Okay, it might be kind of fun now just to look at the graph of this function. So let's get it into our graphing utility, and here's the graph. Okay, there's a few interesting things to note. There's sort of these gaps in the graph. There's sort of this hook, and then it stops. It might be hard to see why we don't get a continuous graph, and there's actually intervals where the function doesn't seem to be defined. Well, there's a cosine function as the base, so it might be better to look at the x-axis rather than in terms of units of 1, maybe look at intervals involving pi or pi by 2. So we can switch how things are labeled on the x-axis by right-clicking on it, going to graphics, x-axis, and what's the unit we want to use? We'd like to use pi. And maybe we'll turn on a distance of every pi by 2, it'll put a tick on the axes. And so now when we look back at the axes, we see that the intervals where the gaps happen are between pi by 2 and 3 pi by 2, 5 pi by 2 and 7 pi by 2. Oh, these are precisely the places where cosine is negative. Why would there be gaps there? Well, if you have a negative base and you're trying to take a rational power of it, a root of it, well, these things won't make sense. You can't take, for example, the square root of a negative number or the fourth root. So these even roots of negative numbers won't exist. So somehow that's being picked up in the graph here. It's not defined here because for these values of x, the base is a negative number. Okay, so we're interested in what happens as the limit as x goes to 0. We see that the value is slightly bigger than 0.6. I want to see if that's e to the negative half. So I'm going to just get it to sketch the horizontal line, y equals e to the negative a half. And there we go. We see that the value at 0, the limiting value at 0, seems to be e to the negative a half, which is what we found through our calculations. So that's a nice picture illustrating what we've actually done computationally. All right, well that's it for this section. Thanks very much for watching, and we'll see you again next time.